All right, good evening, everyone, or good afternoon, everyone. So my name is Wim Mellis. I know that there's a number of people joining online. I like to move around quite a bit. So if those online don't have enough audio from the microphone, then drop something in the chat so I get a signal in here that bounds me a bit more in my place. But other than that, I will be moving around quite a bit. So I'm Wim Mellis. I work with the University of Greenwich in their engineering school. And today I will take you on a bit of a journey which has been part of my research journey around AI systems, and then you will see very quickly where I get to with that. So I will very quickly set the scene with an introduction. What is AI? What a lot of people think is AI and what it isn't. And then I will move over to AI and big data because they're very closely related. What the impact is, and I will take that into what we currently know computing to be, i.e. the platforms on which we run most of this, right? I very much want to do that from the perspective of where the challenges lie with these platforms, because they pretty much determine anything we can do today or can't do, right? I will then move into a bit more on creating artificial a human brain, as you will see very quickly why I make that distinction from where AI sits today. We will see that in a very few slides. And then I will move on to discussing a bit more of the work that some of my PhD students have been working on. So we've been trying new approaches of creating systems that can deliver AI. We've done some of that work in an electronics context. We've done some of that in an optical context, and you will see some examples there. And then I will conclude from there. So throughout this presentation, you will come across a number of lovely animal pictures. So if there's any reason to stay awake, it's at least that one. If you forget about all the other blurs I give, that's forgiven, but enjoy those. AI, artificial intelligence, is very different from where I separated the words artificial and intelligence, right? If we look at the definitions that we've got in dictionaries, then AI very much talks about how to produce machines that can have some of the qualities of us humans, right? A lot of people understand artificial intelligence to be the combination of artificial, i.e. it's made as a copy of something, combined with intelligence, which we know to be the human intelligence, and therefore we assume that the artificial intelligence is exactly the same. Now, it isn't, right? That's the part where we really need to start. So the question then becomes, what does current AI do? It does things like understanding language, recognition of language, recognition of pictures, it's very good at as well. And there's a whole sphere of applications where we're moving into from an AI perspective. I do like this graph because it gives an overview of where some of these applications lie, and they're trying to give an indication of when we can expect some of this to hit the commercial market, so to speak, right? I really want to start here at the right-hand side where you've got computer vision. Computer vision is probably the most developed bit of AI, but we have to be honest that most of the work started in computer vision in the 70s and the 80s. We're 50 years down the line before we now start to see this really hitting the commercial market and become very useful, right? The reason I start there is because that sets a bit of a scene of anything else on that curve. And it equally sets a bit of a scene of why they might have tried to color some of these and say 2 to 5 years all the way to more than 10 years. That is a prediction. If you ask me, it's probably going to take us a bit longer than that, right? But we've got lots of interesting items there. We've got generative AI, very well known from the ChatGPT, and I'll come back to that much later. We've got autonomous vehicles. We keep promising them. They're not going to be here anytime soon. And we see a whole lot of other applications in here as well, right? But underlying all of this is trying to achieve automation of some kind. In many cases, in one application domain, right? And that's another thing we will come back to a bit later. So why do we have these restrictions? What do we have? Why have we managed to get where we are with regards to, for example, computer vision? Because we've had technology improvements from a hardware perspective. The technology has improved between the computers that we had in the 80s and what we have available today, right? But underlying a lot of what's on that curve, computer vision, you know, generative AI, all of these technologies and algorithms were actually developed many decades ago. So from a research perspective, there's still a lot of progress that needs to be made. Now, one thing we need to be conscious of is that that AI system is only going to be as good as the developer or developers that worked on it. You have to be conscious that you're not going to create a system that's better than you, right? So you can bring a pool of developers together, which is going to lead to a better system, but where does that get us to, right? These developers, they create the algorithms that underlie it, and they may be selecting some of that data that's then going to be part of that system as well. And then underlying all of that, because AI is very often seen as the computer science aspect of it, is all the hardware that runs it, right? That's very much where I, as an engineer, come in. Now, as you can see, there's quite a number of layers in between the actual hardware and the actual application running it, right? And so the question is, do we have the right hardware to deliver the applications that we're trying to achieve from an AI perspective? So, AI needs big data. We rely on substantial amounts of data to be able to start doing some of these machine learning tasks, some of these computer vision tasks. Here's a bit of a case study, just to kind of set the scene a bit of what big data really means. So YouTube, known to everyone, YouTube has got approximately 300 hours of video uploaded every single minute. That's quite substantial. That's a statistic that's been standing for a number of years now. If we assume, and this is the only assumption I'm going to make, that that is HD quality, high definition quality, then I come to about a gigabyte per hour. So that's 300 gigabytes per minute added, that's 432 terabytes per day. That's a substantial number, right? Now, this is only a minor fraction of all the data that we as a human society produce on a daily basis. How much of a fraction is that? From 432 terabytes to 3 exabytes, right? If we were to say, okay, we'll develop a system, because all these YouTube videos, how useful are they? We don't know. We don't know until we've looked at them how useful they are. Do they bring us any value? What value do they bring us, etc. Right? So I've got these 300 hours of video per minute added, so that's 432 hours per day. I'm going to set up a company. I'm going to hire people who are going to watch YouTube videos for 8 hours a day. Lovely job. You just watch YouTube videos. Based on that number, I need 54,000 people in my company. That is the current size of Google. Now, this does not leave any time for sick leave, holidays, not even really a proper lunch break. And I haven't really done any classification. So I've watched up the videos, but I haven't done anything with them yet, right? So I probably need more than 54,000 people for this to work. Now, YouTube is only 0.001% of all the data we're producing. So if I was to take this principle and I was to say, okay, I'm going to get humans to analyze all of the data that we're producing, I need 38 billion employees. You can imagine how much more data all of these are going to produce. So this is an endless journey, right? Now, that's also why way less than 1% of all the data being gathered is currently analyzed, right? So where does that put us? Well, let's try and automate. So your human brain will consume, depending on the source, anywhere between 15 to 20 watts equivalent. So if I was to try and build a system that's got the same ability as your human brain, depending again on the source, I will need a computer that will require anywhere from a few hundreds of megawatts to a few gigawatts of power. It will be the size of a football field. One equivalent human, that is, right? So our current research to improve that kind of computing power is aimed to improve by about a factor of 5 by 2030. So that means rather than hundreds of megawatts, I'll be using about 20-30 megawatts, right, by 2030. So there's a bit of a scale of a problem. But then if you put that against the largest power stations on the planet, you can see the largest power station on the planet produces 22.5 gigawatts. Depending on which figures I go with, that's somewhere between tens to a few hundred equivalent humans, right? Houston, I have a problem because I'm not even getting anywhere close to 54,000, let alone 38 billion, right? We can't currently automatically analyze all the data we've got because we haven't got the technology to do it. It's as simple as that. So why is that? Let's have a look at this current digital world. So the digital world is all about ones and zeros, which I have drawn as black and white casts. But then, rather than having just one, I've got loads of them, right? And it doesn't take much to understand that around this point of time, if you have loads of cars together, you get something like that, which is the M25. Pretty much a big parking lot around this time of the day, because I've just got too many of them, right? Computers, in a way, because there's so many bits, it's not that different. So, but we have to go back in history and look at why digital was designed. Digital was actually designed to communicate long distance over a noisy channel, i.e. long distance UK to the States over a noisy channel. Then it becomes very simple because I say yes or no. I don't have all the complications of words, letters, all of that. All those nuances are gone, right? It makes it simple in that context. It works brilliantly for arithmetic and logic operations. That's pretty much the nature of it in itself. But the real question is that what AI requires? Or in other words, does your brain work in the same way? So let's have a further look at some of the trends in computing. 2017, 2015, this hasn't really changed that much after 2015 from a curve perspective. For those old enough to know, around 2005, we stopped talking about processor frequency improvements, which was pretty much linear up to that point. You then bought a new computer every 3 to 4 years because it was way faster. And from that point in time, they figured out they couldn't do that anymore, so they started to sell us multiple core processors. More interesting is that we've also seen a trend in power where we have way more portable devices, and therefore we wanted to see power reduction for those devices as such. And obviously going up, we've been putting loads more transistors onto our silicon because we could, because they became small, right? Now, that then brings us to other challenges around this technology. But as you can see, that power being produced in a smaller area becomes bigger, which means I get a much larger heating problem. I need to get rid of that heat from the silicon. And if I can't do that, that's it. It dies, right? So aside of that, we've just got loads of data. Big data means I've got tons of these casts, i.e. tons of these bits, right? Now, one bit says very little, yes or no. So I need a whole bunch of them to represent something proper, i.e. a letter, let alone a word, let alone do something more than that, right? So personally, I describe that as having a very poor information density. because I need so many bits to do something proper, right? Each bit in its own right doesn't really bring a lot of value, it doesn't bring a lot of content. Altogether, they start to mean something. So my process is very busy with that. They're not necessarily always efficient at dealing with that. Obviously, my communication channels, they fill up very quickly. They're too narrow and so on. And when it comes to memory, it's never big enough. I always want more storage. I always want more working memory, right? Now, where does it end? Is a real question, isn't it? And then on top of that, we've got Moore's law. I mean, what can I do with silicon is put more transistors on there as long as I can keep making them smaller. How much smaller can I make them? Because at some point, I'm starting to work with atom sizes. And if I need to tell one atom on a one atom distance, you need to switch on or switch off, at some point that becomes impossible, right? So that's the challenges we're working against. Now, Moore's law has been set to be ending quite a few times. It will happen at some point, right? When exactly, that's everyone's good guess, right? In the bigger picture, one of the things to think about is actually that all of these bits are interconnected. So the way we represent our data, those bits, are linked with the way we process them, my logical operations, my binary devices and logic, etc., and the way I've implemented it. So as soon as you want to say, okay, I'm going to change one of these, I've got to think about all the other ones, right? And then obviously this equally tells me what applications that platform will be very good at. As I said earlier, arithmetic and logic. So digital hardware and AI, how compatible are they? Question is, do these current computers fit AI requirements? Personally, I don't think they do. Can they deal with huge volumes of data very quickly? They're trying to, but they're not the best way to do it, right? Does the human brain operate using arithmetic and logic functions? If you ask me, no, because we learn arithmetic once we are about an age of 5 or 6 or something like that. So we're not born calculators. We're not born, you know, in the first weeks of our existence starting to tell us, our parents, that 1 + 1 is 2. We learn it at school, right? So it's something that we've inherited and learned. It's not something we're born with. So these brains work in a very different way. On top of that, we've actually, from a design perspective, we created 3 very separate systems and developed them all at different rates, which has caused us a whole bunch of other issues aside as well. So what would I love to have? I would love to have something with cognitive functionality, i.e. real human brain functionality, that consumes about the same amount of power as a human brain. Would be lovely if I can go to 20 watts rather than a few hundred megawatts, because that's a significant factor of difference. It's fast, it's flexible, but that requires me to change things substantially, orders of magnitude difference. And I'm probably not going to get there on the trajectory that I'm currently at, because I will require something very different. Now, if we really want to deal with the big data challenge, then we need that as soon as possible, because the longer it takes, the longer it means we're piling up data somewhere in clouds, data centers, of which we have no clue whether it's got any value at all, right? So, creating that artificial human brain. If we're talking about artificial human brain, I'm really talking about that is different from the current artificial intelligence, right? So I'm really talking about human brain intelligence artificially. So very quickly, human brain's been studied extensively. So many people have said we will understand how the human brain works in the next 5 or 10 years. Some of these are dead already, right? None of them have succeeded doing that in the time span they said they would. So very complex. But what do we know? We know that there is bottom-up models, neural networks, and I'll come to those in a second. And then quite often people are less familiar with some of the work around top-down models, i.e. understanding how it functions as a system, right? And that's the route I will then take you down further. So, neural networks. We've done work on looking at neurons, we've done work on modeling them, we understand that they are so diverse, i.e. most of the neurons in your brain are all different. If one of them dies, it doesn't even get replaced by an identical one. Right? So how can I ever make a reasonable conclusion on how that as a neuron is going to operate, let alone start to make that into a bigger context? Most of these models also look at the electrical aspects, i.e. we look at this as a spike, and in many cases that spike will be simplified to 0, 1, 0. Now, if you ask my electronic engineers with an analog background, they would say, but that's way more complex than your simple on-off. There's loads happening there. Where do we have the value of all that additional information? Where is it gone to if we simplify our system that much? On top of that, the brain isn't purely electrical. There's a lot of chemicals happening there. And these chemicals, for example, related to your emotions, if your emotional state changes, your brain capacity changes, you may make different decisions just based on that emotional change, etc., etc. So what's the impact of all the chemicals on the operations of these neurons? Right. We also know that all of these are flexible interconnections, and they keep flexing. I.e., I can take a snapshot of your brain now at this very instance, and if I wait even less than a fraction of a second longer, it's going to look differently again. So incredibly difficult to understand as a model, let alone start to build up from there, right? Now, having said that, there is work on artificial neural networks. We run these on existing platforms. We are actually creating hardware which looks very similar or attempts to look similar to this. And we have applications that work in this context as well. So not all is bad. But the question is, how good is it going to get, really? So top down, it's very much looking at, okay, I look at the brain as a system. What does it do? How does it work? Right? A few things I know is the brain learns through repetition, i.e. I repeat the same message over and over at a regular pace and you will remember it. Something you see so much in education is something you see so much in different contexts. Now, that's I would call the long way of learning. The experienced one is the short and quick way of learning. You've touched a hot surface, you figured out it's a hot surface, you will remember that, right? You won't repeat the same mistake twice. So that's the quick way of learning. The other thing we do is we're very good at recognizing patterns. Very efficient at recognizing patterns. What is similar, what is different? Where do we see patterns that we recognize? So I look at this room and I recognize a whole bunch of faces. Doesn't take me long to identify the faces. My brain can very quickly focus on that. We don't only do that in space, i.e. I see this room and on these faces, we also do it in time. Best example here is you hear the first few fractions of a second of the song and you go, that's the song. You've recognized that pattern in time, i.e. the sequence of the notes, the music, whatever you want to call it, and you go, that's it. Now combine the two and you've got an incredibly powerful recognizer. Right? Part of where we are. So, other way of describing this is people would say the human brain is a large associative memory. What does that mean? Well, it means it associates incoming information i.e. what you perceive through your senses, with experiences from the past. So, if I was to ask any of you, and this is more about how that data is being stored in that brain, if I was to ask any of you, what did you do last Friday at 4 o'clock? Most of you would start scratching your head because you'd go, Friday? Last Friday? 4 o'clock exactly. What a nightmare. What you do is you then might go to your calendar, try and see, what was on my calendar and start to work your way back. You're trying to find your sequence, your pattern of storing. If, on the other hand, I would say, okay, what did you do the last time you went to the beach? Most people would start telling you a story. Oh, we took the dog along, we went with the whole family and a few additional friends, and it was a really nice and sunny day, and we had ice cream, the whole lot. And that going to the beach for most people would have been longer than last Friday. So that means that you're storing that information based on these experiences. You're not cataloging it like a current computer would do and say, Friday, 4 o'clock, task. Right? Now, if I turn that around, that becomes very powerful as a system again, recognizing what I've learned before, either in space or in time, and seeing how useful that is moving forward. So we've very much looked at developing systems that follow this top-down approach. How do you achieve human brain functionality, or at least part of that, from that top-down model? And how do you then start implementing that in existing technologies? So we've looked at doing some of that in electronics. We've looked at doing some of that in optics. And we will hopefully one day look at doing some of that in quantum. Right. So I will now cycle into the electronics bit. And don't worry, I'm not going to go into a lot of details. I'm not going to show you circuits or any of that. That's not the aim. What we actually found interesting, and this is where the sound of music comes in, is the technology that we were trying out to see, can we quickly identify patterns? Can we quickly recognize stuff that we've learned before? Actually turned out to be very powerful for other contexts as well. And this is the example I will focus on. So we were trying to build better computers. We actually figured out we've got a system that can help us with other applications like better hearing, better cochlear implants, as well as doing things like high quality fidelity audio compression. So how can I store audio very effectively without losing any of the quality? Most people are aware of MP3 players, but the quality of them, if you're really good high fidelity audio expert, you don't like it because it's not very good. Because what happens is you actually throw away a lot of the information, right? It's based on a psychoacoustic model because there are certain sounds that as a human you would not be hearing. For example, a really soft sound after a really loud one, right? So what happens is I take that away. That's information I can throw, allows me with compression. However, that bigger picture changes, right? So when I listen to MP3 songs, I very much notice that, for example, the bass isn't as punchy as it is in the normal recording, right? And that's because you're hiding some of that additional information that otherwise was there. So wouldn't it be lovely if you could still compress, but retain that same quality, right? So from a cochlear implant perspective, what you do is you take the sound, you want to bring it to the brain. You want to first understand what that audio is. Currently, what we do, fast Fourier transform. It's the only way pretty much that we can do it. Wavelet transforms, another way of doing it. They have their limitations, i.e. they throw away some of the information, right? I will quickly show you what that means in the demo. But once you've done that, you then understand what the audio signal is, i.e. Someone speaking to me? Am I listening to music? What is it? Right? How do I turn that into a spike pattern that can then be linked into the brain? Because the brain speaks some kind of spike language. And if we're brutally honest about it, we don't fully understand it yet. Right? Current cochlear implants for many people changed their life. Lots of musicians have to give up their career because the current cochlear implants are that poor. Now, let me kind of show you what that means in practice. So I will play you a few samples. I will start off each time with the original sound. I will then play you a simulated version of the current cochlear implant, i.e. the signal that would be received by the brain, right? There is a reason why people with cochlear implants have to go through quite a bit of training, because you will notice that they need to learn to re-understand the signal they're receiving. And I will then play you an equivalent running it through our system, right? Now, this very much focuses on that first bit, the audio decomposition, i.e. what do I still have left before I send it into the spiker, right? So first example, I'll play you two different sets. So this is a piece of violin music. So what you heard there just before the last few seconds was the original, right? I need to unhide my play button a bit more, but there we go. This is what the current cochlear implant makes of that. So good luck if you can recognize the two out of one another, right? Moving on, this is what our audio decomposition makes of that. For most people, the difference will be hardly noticeable. In numbers, current cochlear implants lose about 90% of the original signal. Our system retains more than 90% of the original signal. So I'll give you a second one, which is the vocal one, so you understand a bit more the difference when it comes to the human voice. Original.
I love my life for you.
And then we got current cochlear implant. If you listen very carefully, you can hear the kind of areas where the voice is pronouncing, right? And because you know what was coming, you could kind of get some of that out there. Last one.
I love my life for you.
So this is just kind of setting a bit of a scene of how certain technologies, as you develop them, can have benefits in other areas. Over to the other side, optical recognition. So what we present, or what I will present here, is one of the two ways of doing optical recognition. I say one of the two, the second one I can't quite talk about from an intellectual property perspective. But this is just showing you a bit of an example of what you can do in the optical field. Very standard, very easy, very comfortable, which if you were to use a standard digital computer would consume a lot of power to do it. All right. So here we go. So this isn't unknown, optical cross-correlation. So cross-correlation is a technique to identify input compared with a bunch of items, which one's the closest batch, right? My associative memory approach, remember? I can do this in the optical domain. Now, what's the benefits of doing this optically? Well, I can do it in 2D and 3D all in one go. It's just one of the benefits. But I've got a bit of a challenge to overcome then. I might take an input, compare it with stored data, as you can see, these are different approaches to cross-correlation, but I will hit all of them at the same rate. I.e., I get a number out of that, or I get some kind of output that says how similar it is. So you can see in the second example, I've lost an eye, therefore I've got an impact on these not being as big as they used to be because it's not exactly the same. It's close, but it's not exact. Again, I've added a nose, and I can see now that I've got some differences here as well. What more can I do? Well, I can easily identify an object out of a whole series of objects. Optical cross-correlation, as you can see, I can see some of these are getting there. They have similarity, but it really peaks here, which is where it stands. Now, you could even say, well, why are some of these other ones very close? You can start to see that some of the detail there has got similarity, right? So if I'm looking for a system that's very quickly going to get me in the right direction of something I'm looking for, I'm on the right track. Now, I can then start to play with some of the optical elements of, okay, so how do I deal with challenges of my object being moved around? I've got an autonomous vehicle. My pedestrian could be anywhere in my view. It might be 10 meters away, it might be just in front of my car. I still need to recognize them all, right? So can I do that? Yes, I can move to what we call the Fourier domain, the frequency domain, and I can work there. Because independent of the location of that object, if I'm in the Fourier domain, it's the same. So that allows me to very quickly identify an object in the scene, independent of where it is. i.e., I'm interested to know whether there's a pedestrian there, because if there's none, it's very different, right? If I can do that very quickly, I've got benefit. I can do edge detection by going into the Fourier domain, then filtering out what we call the DC component, the lower frequencies. So I can do filtering very easily, because all I need to do is block the light here in the center, and I've got an edge detector. Trying to do edge detection on a computer, I will have to run through all of these and identify whether the neighboring pixels are different or not. If they're different, okay, I might have an edge. Some of the other challenges is I know that objects are barely ever going to be identical to the database. They might have different size, they might have slightly different rotation, and so on and so forth. So how do I deal with that? If they're different size, you can see I identify the one with the same size very quickly, but I can equally see that that one's not too far off. And this one's again got similarity because if I look at the really tiny bits of detail, I can start to recognize some of that. So I've got a mechanism here that's going to very quickly tell me what I've got there. I may then have to identify where it is and how different it is if that's relevant, but that's not always necessary, right? What I do need to take into account is how am I going to work with all of these differences: orientation, positional differences, scaling, larger, smaller, color differences, if I start to work in the color sphere, additions, removals of details, and so on and so forth. But I can do all of that in the optical domain. So this is a similar simulation, but in a different platform. I've got the letter going in, I've got my Fourier lens to bring it into the Fourier domain, and then I need to come back to the original domain. This is actually comparing that with itself. And then here I've got that same letter, which I scaled a bit, just to see that the output is impacted by the slight differences of scale, right? But I need to understand what these differences are in output and how that relates to the differences between the inputs. And then from the simulations, we moved into the lab. So these are experiments done in a laser lab. You look at input, Fourier transform. These are done in the laser lab. These are actually the simulated versions just to show that the simulations were correct. But I've taken these two because you can see that the level of detail that I've got here has got similarity to this, which means that I've got similarities in the frequency domain as well, right? Once again, I can decide to move away, take the DC component, start to play with loads of that. So I've then taken this element, compared it with my database, and guess who lights up? The right item. Demonstration of doing edge detection in the laser lab. You take the input object, I've nicely got my edges detected there. All optically, all done in real time. Why would I spend so much energy on a digital machine trying to do all of that if I can do it real time in the optical domain? Especially if my input is optical anyway, right? So this demonstrates that you can do very efficient processing on, for example, images to identify similarities, differences, identify whether objects are there or not, and so on and so forth. For me, that's the base layer of how you can then start to build a system that does that. So we obviously still need to work from these basic principles into a system. How do you combine that? How do you move into a real application? We have thought about storage, and that's very much where our second approach comes in, but I'm not going to talk about that one here. And one day I really want to move into quantum, because if we can do whatever we've done in electronics, which is the same approach as what we're using in optics, then I can guarantee you we can do it in quantum. And that's really where, for me, then the whole sphere and the power comes up. So in conclusion, AI systems, I fear to say they're limited by the output and development, they're limited by the data that's being used, and they're limited by the technologies that we've got to run them on. But they're unlikely to also get us to a real, what we call, artificial human being. They're limited equally in their generating abilities. I said I was going to come back to ChatGPT. ChatGPT is one of those generative AI technologies. One of the challenges is it's only as good as its data set. This is very different from creative work. And there's a reason it's called generative AI, not creative AI. A lot of people have assumed that this is creative. It is in no way creative. And if we're not careful, it's going to kill creativity. Because if we assume that this is the source of everything, which is what some people start to say, it will actually kill creativity, because we think it's the source of everything. So I fear to say, as contrary to quite a few others, I think AI is massively oversold in what it can do, because we still have a very long way to go to make it really do that properly in many cases. So, equally, reaching human intelligence artificially will require the development of very new computing platforms who can deal with large data sets quickly and efficiently, who can process that data without needing to convert it into something like the digital domain. Why can't I process images in the image domain? For Christ's sake, why do I have to convert all of them to the digital domain? It seems bonkers to me. And one of the biggest challenges, and a bit of a moan for me at the very end, it seems very little recognized that all of this work is essential if we want to move this field onwards. Because believe it or not, but it's incredibly hard to get any funding for something that isn't digital. That's it for me. Thank you for listening, watching. A special thanks to my PhD students who are either there or not there, depending on the doctor in front of them. But any questions? And it's probably best to take questions in the room first, and then we'll move over to those who meanwhile have managed to type them out online. By the way. No? No one's going to fire away? trying to get to the questions. Okay, right. Right, so let's go with the questions on the online then. How can AI help us with our assignments? Coming back to generative AI and ChatGPT, I think there is value in presenting the right information to the person at the right time. There is equally a need to understand what the limitations of that are as a platform. i.e., if you expect ChatGPT to do the job for you, then why are you still here? Every single human being has got a role to play on this planet, which is where I come from. Every single human being is different for that very same reason. And so, as far as I'm concerned, use ChatGPT as a source, just like you use Google. But be careful, it's not the answer to everything. Right? Your brain is still way more capable than what ChatGPT will ever do in the next 10 years. And as they say, use it or lose it. So be careful. How accurate is ChatGPT and can we trust it? Accuracy is a very tricky word to use in this context. It is as good as the data it's used to learn, is what I would say. And you have to be conscious that ChatGPT, I think version 3, which is the openly available free version, stopped to learn somewhere in 2021. So there's a restriction there on what it learns. The new one, ChatGPT 4, for which you can get a paid license access, is more up to date, and this will, continue to improve. The question is, how far or how much better will it get? Because it all depends on the data going in. Right? That's what these platforms are. I'm talking about ChatGPT. I throw ChatGPT, bars, all of them. I throw them all in the same bucket because they're all very similar from underlying technology as well as data perspective. Right? I would equally like to say that a lot of the underlying technologies, believe it or not, that basically lie at the origin of what's now your ChatGPT dates back to the 1980s. So what people now call machine learning, deep learning, it's just a relabeling of names. For those people interested in knowledge exchange and how knowledge travels across, people, etc., and there's a very interesting book, I think it's called Scientific Revolutions, and it very much talks about everything being sine waves, everything going through ups and downs. So every single field will have an up, and then it will go and die and come back. What would be interesting to do, and I don't think anyone's done it so far, is actually compare these scientific revolutions and their periods of how quickly they happen with human generations. Because a lot of work gets repeated, because no one gets as bothered enough to read what's happened 20 years ago, because they think it's old news. It's not. I think we can consider that one answered. There's a question in the room which I'm going to give priority to. I'll come back to the other ones in a second.
I was curious about the artificial generative. Is it the same as generative AI or is it different?
So generative AI is really more about how do I take this data to make a useful answer to you, right? So this is where you can see the interactive stuff with ChatGPT. You can interact with it, you can steer it, you can kind of direct it a bit more to giving you useful output. General AI, I think, is trying to kind of probably go down the route of what we call general computing, trying to do everything in one go. And the challenge with doing everything in one go is how good are you ever going to get at it, right? If you look at most AI applications, the reasons they work is because they're extremely limited in what they say they're going to do. They're either a text to speech converter. They're a human recognizer based on your voice. They are a object recognizer that recognizes X number of objects, etc., etc. The real challenge we've got is how do you open that up to dealing with a whole bunch of different applications and still be good at it, right? Next question. How close is AI to human intelligence? Personally, I would say it's still very far away. We do subsets of it, right? Take an example, text to speech. Sorry, speech to text. So I speak to a system and it will turn it into text. These systems have been around for quite a number of decades. They are getting better. We all know them through Siri, systems like that. The reasons they get better is because as you use them, they gather your data to try and make the system even better, right? Is it 100% accurate? No, it's not. Is a human 100% accurate? No, he or she never will be, right? But there's a tricky part here in the sense that as humans, we haven't quite got it. What we tend to do is we tend to use the context of the conversation, context of the environment, previous parts of the sentence to fill up the gaps. These systems can't fill up these gaps, right? And you have to equally consider, you know, what is a good accuracy. An example that a colleague of mine used to say is, if I have a speech recognizer that is 90% accurate, and I have to dictate it a 10-digit phone number, it will get it wrong every single time, because I always have one digit which is wrong. So as a system, it's not useful, right? Leads to frustration, and you go the whole way from there. So AI as it stands, good at certain applications. Are we going to get better at some of these? I think we're going to be putting a lot of effort in for very marginal improvements. That's my opinion on it. Next question, I think. How do you see the role of quantum computing and the role of AI? I'm assuming that's quantum computing in the context of AI a bit more. So quantum computing, optical computing, as we know them, they're all based on the digital principles. They're not. So from where I sit, when I've presented you optical computing, for me, that's optical computing using the whole abilities of optical sphere. You use the light as it is, you use the different frequencies, i.e. the different colors, you use all of that. Optical computing, as it is being developed by most, is an advanced digital system. The same with quantum computing, right? The real benefit of quantum computing versus the other two, i.e. electronics or optics based, is that rather than having that 1 or a 0, I can now somewhere sit on the probability of a 1 and a 0. I could do that range, so I can bring a whole bunch of combinations together into one calculation, which makes it faster. So it's the parallelism of all these combinations which makes quantum computer faster, right? Is it going to speed up data processing? From that perspective, yes. Is it going to deal with larger data rates? If we can get the data to it quickly enough, let's see, right? Because that's where the challenge will lie. And that's currently where the challenge lies as well. For anyone who's ever heard of the von Neumann bottleneck, the real problem these days is not the processor, it's getting the data to the processor quickly enough, right? If I can't get the data to the processor quickly enough, the processor just sits there, twiddles its thumbs, says, what have you got for me, right? And so it's about getting that memory and communication to be, as good as and as quick enough to be feeding that processor with data. Now, that applies to general purpose computing. That applies to a lot of what I would call digital design contexts. So as an electronic engineer, I would say if you currently design a application, could be a chip, could be anything, your biggest challenge is going to get that data to the right place at the right time. That's where you will spend most of your design time on, right? Which raises, for me, some challenges into how we do these designs as well. I'm going to take a question from the room in between.
Yes, like I wanted to find out whether in generating AI, whether it is screening or like correction happening. How, if it's happening, how does
So that would depend on the data selection and the data they're using. I think these days in a lot of these systems, the data that's being used to train these systems is automatically gathered.
right? Models?
Exactly how they monitor the quality of the data, I'm not that familiar with. But a good example of the other end is for anyone who's ever heard of IBM Watson as a system. So IBM Watson is known through the media because it won the Jeopardy Challenge, which is a big quiz in the US a number of years ago. Right? So as a system, IBM engineers worked on that for probably 5 to 10 years with a team of about 20 people. Right? That was designing the system, i.e. the technology, as well as selecting all the data sources, making sure they were good quality, etc., etc. Right? So there was a huge amount of human investment in making sure that the data that was within that system of a good quality. Right? It won the challenge not because it was better, but it was slightly quicker. And with that, I mean, you as a human have a bit of a delay between, yes, I know that, and pressing the buzzer. That delay is on average about 18 milliseconds. So if you go, yep, right, by the time you've pressed that button, you've lost 18 milliseconds. The benefit of the IBM Watson was it didn't need the 18 milliseconds, so it was slightly quicker at pressing the buzzer, and that's why it won, not because it was smarter. Right? Not something IBM obviously likes to admit to. These days, I think a lot more is being done on how to automatically judge some of that information, although that's not an easy task, and I think they do it based on popularity and you know, recurrence of data sets, etc., etc. Yeah. But as with anything, you know, it all depends on who your source or what your source is. Do you think AGI, artificial general intelligence, is going to be available soon, and how influential could it be? Well, depends on your definition of soon, I think. I think we will see stuff appearing in this sphere. How good it will be when it first comes to the market is probably as good as anyone's guess for now. Depending on, I mean, we've all seen that when ChatGPT launched, very quickly after that, Google went, we need to be on Sphere as well, right? So if someone tries to hit the market, someone else will try and follow. Does that mean that, I mean, the reason Google hadn't launched it was because they didn't thought it was good enough, but then they didn't want to lose out on the competition either. So there's a bit of a competitive game happening there. I'm not going to be predicting and saying this is going to happen in the next 2 years and this is going to be X, Y, and Z good, because anyone's guess is as good, I think. And you know, all what would happen is someone would come back to me in 2 years' time and say you were wrong. So I'm not going to go down that route. Sorry. Any other questions? I have no idea what timing we've got because I haven't got a clock anywhere. 5 o'clock? Right, okay. So if there's no further questions, and for some